Ismafairus.
Dr. Aini Ismafairus is a lecturer in the Department of Neuroscience, University Science Malaysia. She obtained her PhD in neuroscience in Germany in the year 2016. She has numerous publications with special interest in functional MRI, visual and working memory, cognitive neurosciences, non-invasive brain stimulation, and plasticity.
Majelis dengan segala hormatnya menjemput dan mempersilakan.
Assalamualaikum and very good morning to everyone. First of all, I would like to apologize if sometimes you can hear my short breath and coughing because I'm still recovering from my upper respiratory tract infection and also dengue fever. So apology for that. So yeah, before we start, for my topic, statistical inference in FMRI, I would like to know how many of you have knowledge and even experience with the FMRI. Can you raise your hand, especially for those in the hall? 1, 2, 3, 4. Okay, thank you. 5. All right. So we will start with the statistical inference in FMRI, which is this is one of the important techniques, especially to get the brain activation after you do the pre-processing method. So I hope that in this topic, okay, you are able to understand statistical inference in FMRI, and at the same time, you know how to select the correction method, especially for multiple comparison. So as for introduction, we know that FMRI, okay, is one of the methods that we can use to explore brain function, okay, and FMRI. We also can help us to know many activation related to clinical, but also in research area. You have heard about the theory of the FMRI from Dr. Priya, and also you have learned about the neurodegeneration. So let's say if we apply, okay, all those things by using FMRI method to explore dementia, Alzheimer, for example, in terms of the function. So the most important part is the statistical inference other than the pre-processing method, because the statistical inference help you to actually, okay, report your findings. So the goal of statistical approach is to identify actual brain activation from false alarm, because we know that in statistical method, we have type 1 and type 2 errors, okay? So we hope that by using a proper selection of statistical approach, we are able to reduce both false negative and false positive rates. So statistical inference, also known as set level inference, which is the number of cluster comprising and occurred by chance. Because when we discuss about the FMRI, usually you will read in the textbooks or articles, they discuss about the voxels, okay, cluster levels. So we will touch on that later on. Okay. So we want to identify activation in statistical parametric maps and taking into account the relative sensitivity of degree of inference, which is at the voxel level, cluster level, and also set level. Okay, I will further explain later on. So based on this thing, okay, the probability to obtain the statistical activation, yes, of course, we need to actually focus on the voxels and also cluster. For FMRI, because the statistical method not only apply in FMRI, but also you can apply in other methods, PET, CT, EEG. Okay, but for FMRI, the statistical process that follow are often defined in terms of regional executions over some threshold. That's why when you want to do a statistical analysis, especially after you do a contrast manager. Okay, you need to set your p-value, whether it's p-value equals to 0.05, p-value equals to 0.001. So in 2019, Han et al. From the University of Alabama mentioned that accounting for multiple comparison in fMRI studies to eliminate false positive has been a series between hundreds of thousands of brain voxels. Okay, why? Because of if you do a simple statistical analysis, for example, if you want to compare blood pressure between male and female, okay, in terms of the number of participants, maybe it will not achieve up to 100,000 participants. But in fMRI, when we do a measurement, we talk about voxels. So in our brain, it contains thousands of voxels. And how we analyze the data, whether we need to analyze the voxel individually, independently, or actually dependently. So it seems like we need to analyze the data because we know that every voxel, we usually measure in time series because we have a lot of tasks, okay, given. So it's very complex in fMRI. So we need to actually analyze the data carefully so that we manage to avoid misleading in terms of the results, especially in the false positive rate. Okay, what is false negative and what is a false positive? In fMRI research, a false negative, also known as type 2 error. Okay, the same thing if you do outside the fMRI research, we know that false negative is type 2 error, which is for fMRI refers to the failure to detect true brain activation that is present in the data. Okay, so findings of the analysis fail to identify the activation in specific brain area when there is actual data, actual brain activation. Okay, so means that we cannot detect even though there is actual brain activation there. So this might be due to the number of factors. One of it is the small sample size. Okay, and then lack of statistical power. That's why when you want, especially if you want to do a research study, before you do your research proposal, or while you are doing research proposal, you need to calculate the sample size by putting a proper value for powers and then p-values, for example. Okay, so means that you can have enough number. Other than that, it might also due to limitations of the imaging technology itself. For MRI, we know that we have a different magnetic field. Okay, if you choose 1.5 Tesla, it might be different if you use 3.0 Tesla, and even 7 Tesla, because we know that in terms of the resolution, it might be different. Okay, this might also one of the reasons why sometimes you can't detect the activation. Okay, for false positive in fMRI research, a false positive also known as type 1 error, which is refers to the detections of apparent brain activation that is not actually present in the data. Findings of the analysis imply the existence of activation in specific brain area where there is no activation. This might be due to variety of issues as well. One of it because of the data noise or even of the artifacts. For those who have a knowledge on fMRI, you know that for fMRI, usually, or even MRI, we usually advise our patient or participant to stay still. Because if not, you will get artifact from the result and misleading in terms of the finding. For fMRI, if you still remember, during the realignment process, we usually do motion correction, right? So it means that this is one of the method that we apply so that we can try to reduce the issue related to the false positive as well. Other than we will discuss further after this, which is related to smoothing and so on. Okay, so yeah, for the artifacts for fMRI, usually we do a motion correction in 6 parameters, which is in X, Y, Z, pitch, roll, yaw. Okay, so this is one of the method that we apply as well. So in fMRI, both false positive and false negative error can have a big effect. Okay, and they can lead to a wrong ideas, especially when you want to interpret the data. So to avoid this mistake, usually you need to set the right statistical threshold. Either you need to choose 0.001 or you need to choose 0.005 or 0.5 and so on. But based on the literature review, especially related to fMRI study, one of the study from Worsley, if I'm not mistaken, suggested to actually choose the p-value which is less than 0.2. Okay, and it's advisable to use 0.5 and 0.001. So in terms of the multiple comparison correction, FWE and also FDR, which is family-wise error, and also false discovery rate, are the method that usually used, but mostly people use FWE instead of FDR. Okay, when we talk about statistical inference, it's actually related with hypothesis testing and also p-value, like I mentioned about the p-value, okay, before this. So the null hypothesis is evaluated using a test statistic, which is we would like to see or show the effect of interest. Okay, in terms of the fMRI, for example, if we give our participant or even patient in the hospital, for example, if you want to explore the working memory, you want to know which area is actually light up when you give N-back task, for example, which is a well-known working memory method, not only in fMRI, but also I think in psychology as well. So means that we want to see the effect, okay, from the N-back task itself, so that we know where is the location, okay, for that specific task. Because fMRI is very specific. If you want to actually explore motor, so means that you have to give a motor task to the participant so that you know which area involved, okay? Also for other cognitive function. So the observed statistic is compared to its distribution under the null hypothesis, producing a p-value. So we want to see whether, you know, there is activation, whether there is an effect or there is no effect. So means that we have to know what is our null hypothesis, what is our alternative hypothesis. So if we choose a very small p-value, okay, a small p-value is interpreted as indicating that there is a little support for the null hypothesis, though its interpretation is more subtle. Okay, so the p-value is probability of observing statistical value as large or larger under an identical replications of the experiment and under the assumption that the null hypothesis is true. So hence the p-value is a statement about the data. So means that hypothesis and also p-value is related. So that's why if you, especially for research, if you want to do your objective, okay, you have to know what statistic that you want to apply before you did it, because we need to know what are the variables that we need to actually apply. And because we worried that if you do the experiment without looking at your objective and the statistical method, we worried that you actually miss some of the variables, okay, that could lead to misinterpretation. Because we know that when involved in research, let's say in clinical, because clinical is case series, I mean only one case, but if you do a research to in terms of the fundamental or you want to know more details, so you have, like, for example, gender, males, female, and then other than that, maybe you have a few other variables. Okay, let's say the IQ level. Okay, other than that, maybe you have blood pressure level, for example. So means that if you miss some of the important information, might be, you know, it will not support your finding. Why did this happen, even though you choose a proper methodology in terms of the statistical inference? So yeah, in the decision theoretic framework of hypothesis testing, pre-specific significant level is used to accept or reject the null hypothesis. So means that we need to set our critical value, which is the alpha. Okay, so that you can apply that during your analysis, statistical inference. So for fMRI, usually we talk about the false positive rate. Okay, and then for the false negative rate is the beta, which is the statistical power. So if you want to actually focus on the statistical power, you can try to look into the false negative. Okay, But if you're actually interested in terms of the brain activation, especially in the social science, usually people focus on the false positive rate. I mean, in terms of the selection of multiple comparison, okay, correction. That's why people choose FWE, especially to tackle the false positive rate. But some cases, they will choose FDR to tackle for the false negative rate as well. Okay, so statistical power is the probability of rejecting the null hypothesis when it is false. So what it would seem natural to focus attention to the power of the test. Power is the functions of the unknown alternative, and the best that can be done is to use test statistics that maximize power over all alternative. So yeah, in general, power of test increase with the sample size. So this is related to the degree of freedom as well. So means that if you want to have enough power, you have to have enough sample size. How to calculate? Like I mentioned previously, during your sample size calculation, for FMRI, usually we choose 80% power, 95% confidence intervals. In terms of the p-value, you can choose either 0.05 or 0.001. And usually in terms of the effect size, I found a few articles suggest for the effect size value, choose medium effect size. Okay, but it depends also in your task. So means that if you choose certain tasks like motor, maybe some of the publications suggest differently. So means that you can look into their methodology if you actually try to modify or apply the same methodology but with a different population, for example. So you can try looking at the effect size value from that paper. If they didn't put the effect size value, you can calculate from the mean or also standard deviation, and from there you can get the effect size value, and it will help you actually to calculate for the sample size. All right. So now it comes to hypothesis example. Okay, for example, when we do a single t-test, we compare the t-value we have found to the null distribution for the t-statistic. Let's say our t-value is 2.42 and we have 40 degrees of freedom. So the null distribution of the t-statistic with 40 degrees of freedom tells us that the probability of observing a value greater than or equal to 2.42 if there is no effect is only 0.01. Okay, so means that you have to look at the mathematics book in terms of the Aziz score, t-statistic, all right, to know the values, right? In our case, we can reject the null hypothesis with a 1% risk of type 1 error because we choose our p equals to 0.01. Okay, based on the Z selection, based on the t-value statistic. Okay, so chance that we think that we are wrong when we reject the null hypothesis here is 1%. Okay, the situation is more complicated when it comes to functional imaging. You still remember that I mentioned in our brain contains a lot of voxels, not only 50, not only 40, but thousands of voxels. So that's why it's more complicated in terms of this to calculate, especially when it comes to statistical inference. Okay, yeah, and for this, and this is another example when it comes to the voxel, so that you can get the idea how many errors that we can expect if we have 1,000 of voxels. Okay, you actually can get this information from Han et al. 2019. You can just browse the paper and take it from them. Because of the FMRI data involved, okay, hundreds, thousands of voxels. So for example, we have 902,629 voxels in each image. Okay, in each image. So our p-value 0.05. So at the moment, we didn't apply any correction method, either FWE or FDR. Okay, so the likelihood to encounter type 1 error, at least one during the statistical analysis. Sorry, I think when they do the conversion, there is a problem with the equation. Okay, there is equation actually. Because I gave a PDF version when convert to a PowerPoint, maybe change some part. So based on the calculation, it close to 1, okay, which is greater than the initial intended p-value, which is 0.05. So how to calculate the error? Okay, we know that our p-value is 0.05. You know the number of voxels. You can actually times with the p-value. Okay, the number of voxels times the p-value. And then you will get for about 40 plus K errors. So you can see how big is the errors, not so small. Okay. So that's why to encounter this problem in FMRI, we actually apply random field theory method. So the random field theory method, before you apply the statistical inference, you still remember during the SPM analysis for those who have the knowledge in FMRI, we have the first level analysis. Okay, during the first level analysis, you have to design, okay, your task. So means that, for example, if you give n-back task, you know that during the n-back task, maybe you actually introduce the participant and ask them to complete maybe 1 back, 2 back, 3 back. Some of the people, they also put rest as one of the condition. Okay, so this also will actually influence to the analysis, all right? So for example, we just have a very simple tool, task and baseline. Okay, so we want to see the effect of interest or the brain activation during task or task more than baseline, for example. Okay, so we need to calculate the statistic for each voxel based on our contrast manager selection. Okay, so we know that in reality, before you do the first level analysis, for those who have SPM experience and FMRI experience, what is the method we apply? What is the method? You still remember? Before first level analysis, during the pre-processing method. Smoothing, right? So, because of smoothing method applied, okay, if you do one Ferroni correction, we assume our voxels is actually independent. In random field theory, okay, we assume they are actually interrelated. Okay, because we apply because this is Gaussian random field theory. You remember the full half-wave maximum. Okay, we apply this method because we try to blur the voxels. Okay, the simple thing, let's say you selfie, okay, and then you apply a correction method during selfie so that your pimple can be blurred. So we can't see the pimple. So this is what happened during smoothing, okay? Similar to FMRI, because we know that the brain activation is like a dot, 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 dot. But we know that actually one to another voxel is actually related. Okay, that's why we apply the smoothing method. And because it's a complex process in FMRI, random field theory is a reason mathematics method that we can actually apply because we apply smooth statistical maths. Okay, so for this one, when we talk about random field theory, it's actually relate with the Euler characteristic. Okay, the way that RFT solve this problem is by using result that give the expected Euler characteristic for a smooth statistical map. Okay, so it's actually related with the smoothing method. That's why there is a stages when you want to apply RFT method, random field theory. First, the data has been smooth, which is we call it partial correlation. Okay, and then from there, it will calculate the expected Euler characteristic at different threshold. Why different threshold? It depends. If you choose 0.001 or 0.05, it will actually give you a different brain activation in terms of the number of voxels. Okay. So this is one of the examples. Okay, so let's say this is the smooth data. This is without the applications of statistical inference, which is you still didn't threshold using p-value 0.05 or 0.001. But this one we apply, okay, different Z-score value. Okay, so figure 3 Okay, this is figure 3, the smooth data, and this is the figure 4, and this is the figure 5. Okay, for figure 4, the value, we can see there is a 3 blocks, but figure 1 is only 1 block because we apply different Z-score value and also p-value. Okay, when we thresholded our data. So when we talk about corrected p-value, if you still remember, during your analysis, they will ask you to choose uncorrected or FWE. So uncorrected, it seems like one for any correction. Okay, you even can refer at the SPM 12 manual. If I'm not mistaken, page 284, they give you a suggestion or example. Okay, let's say you have 100,000 of voxels and you choose p-value 0.001. So means that you need to divide, okay, your number of voxels 0.01, I will show you later on. I think 0.001 divided by the 1,000 voxels, then you can get the exact p-value and then you can check on the z-score, everything. All right. So, but the uncorrected, it treat the data independently. But the random field theory, it seems like a family. Okay, because during the FWHM, we select certain value. Maybe some of you just use default, which is 888. Okay, so this is related with a resolution element. Okay, I think for those we didn't familiar with resolution element, when we talk about picture, it's related with pixels. Okay, so which is the number of blocks in the pictures. But in FMRI, we talk about resolution elements, either 2D or 3D. Okay, so we try to smooth the data based on the FWHM values. So this is the example of the Euler characteristic if we are having 100 results. So what is the Z threshold? So from here, it's actually, this is related to how many, I mean, in terms of the brain activation. Okay, let's say you choose P equals to 0.01 and the Z value is X at X, and then any brain activation, okay, any voxels that actually have Z value above 2.5, it will appear in the brain mass. Below than that, it will not appear in the brain activation. So this is the example, okay? If you choose one for any correction and also a random field theory. Okay. So if you choose an uncorrected p-value, let's say you choose the p-value is 0.05 and you have 100 voxels only or 100 results, okay, 0.05 will divide it by 100 and from that value you will get the z-score. But the random field theory, because we apply smooth technique, okay, so the z value is different compared to the z value in one for any correction. Okay, because this is corrected method, this is uncorrected method. So for the uncorrected method, you have to be careful in terms of selections of the p-value. Most of the publication, they suggest to choose p-value 0.001. Okay, remember, during your p-value 0.001 uncorrected or FWE selection, during your statistical inference stage, okay, they actually focus on the voxels level, not the cluster level. If you want to do a cluster level, you have to apply, okay, cluster level multiple comparisons correction. So for the correction, we can correct them at voxels or at cluster level. So when we want to select, we have to be make sure in terms of the sensitivity and also the specificity. Okay, when we set to a high level test, okay, intensity of the voxels, because we know that, okay, the p-value, so means that we need to actually properly select so that we know the z-score above what value they were interested in. But in FMRI, you have to take note, when we talk about statistical inference, actually, most of the experts suggest if you have a pre-knowledge in terms of the regions of interest. because if not, it seems like we measure the whole brain volume, and in terms of the degree of freedom, it increase. Okay, if you have already have a pre-knowledge, let's say in your objective, you expected that the frontal parietal area, maybe the dorsolateral prefrontal cortex, is activated when you analyze and backcast, for example. Okay, so means that you only focus on this area, dorsolateral prefrontal cortex. So in terms of the number of vox cells, it will be reduced compared to the whole volume, right? So means that in terms of the statistical inference, we know that each voxel contain statistics. So means that we need to do the statistic for each voxel. So we try to reduce the degree of freedom so that you can actually get a better finding in terms of that if you already have a pre-knowledge. That's why it's advisable by the expert that if you already know what region you want to explore. If you didn't know, then you have to explore the whole volume of brain. Okay, that's why it will increase the degree of freedom. So for the family-wise error and post-discovery rate, okay, family-wise error correction, if we use random field theory, so means that when you do a selection during the SPM analysis, especially, you choose FWE. Okay, but if you choose uncorrected, like I mentioned previously, it seems like related to bone corollary correction. So most of the researchers suggest use FWE, but in some cases, especially in clinical finding, I found that a lot of papers, they choose full discovery rate. This is because of maybe sometimes we hard to find enough samples, but we know that we control the power. Okay, so that's why we choose FDR. Okay, but you have, I mean, you as a researcher or you as a doctor, you can select, but some cases maybe you cannot apply correction method because there is no activation. Okay, then you have to choose uncorrected. But for uncorrected, it's advisable to actually use p-value 0.001, not 0.05. If you choose FWE, then okay, if you want to select FWE at 0.005 for the p-value. Okay, so, but for FDR, most of the experts suggest you have to take care when you want to apply this method. Okay, because this is more in terms of the false negative. But for FWE, we know that FMRI more in terms of the false positive rate. That's why usually people choose FWE. Okay, and then I would like to show you what is the difference between peak level and cluster level. Okay, I'm not sure whether you can see clearly. Okay, let's say we didn't apply any correction method, which is you can see here, p-value 0.001 uncorrected. This is at voxel level, but you also can actually use cluster level correction. Okay, maybe because of your data, I mean, didn't give any brain activation when you choose FWE. Okay, you can select uncorrected, but it's advisable to actually apply correction method during the cluster level. How to do it? You can check below here, the information. Can you see there is FWEC and FDRC? C means cluster. Okay, so let's say you choose FWE correction. So when you want to write your report, you can actually write, you thresholded your data at voxel level, P uncorrected 0.01 with cluster level correction, PFWE 0.05, for example. Okay, or FWE-X, because we choose the number of voxels here, FWE with 177 voxels that we actually do the extent threshold. So this is the extent threshold 0. And then when you apply cluster correction, we actually, do you still remember there is a selection P uncorrected and then FWE. Let's say you choose uncorrected and then they ask you about the extent threshold. So you can choose extent threshold 177. So it seems like here you actually apply both voxel level and cluster level. So you can report you thresholded your data at voxel level 0.001 uncorrected with FWE correction at 177 voxels. Okay, so when you do the cluster correction, okay, by putting 177 voxels, you can see the differences, right? So more voxels here and less voxels here. So means that we apply the RFT method but at cluster level. Okay, and also this is some other method. If you also can apply FWE correction at voxel level and cluster level. So you just need to check what is the FWE cluster level value. So here they suggest 1 voxels. So means that you need to include extent threshold 1 with the FWE correction 0.05, right? Similar to FDR. Okay. So in conclusion, for FMRI, usually for the correction for multiple testing, we usually take care in terms of the false positive rate. Okay, so in terms of the random field theory, okay, you can actually apply the FWE or FDR correction at voxels and cluster level. But remember, for FDR, you have to interpret it with care because it's less specific and more sensitive because we increase power to detect the true effect. But in terms of the FWE, it's very specific but not so sensitive because of maybe if you have less sample size, for example. So it's great to apply FWE if you have a large sample size. I think with that all, thank you.
Majlis, terima kasih kepada Dr. Aini Ismafairus atas ceramah yang disampaikan.